Hello everybody, and welcome to the Collisions Post-Lab. So what we're trying to do here is to determine how does the initial system momentum compare to the final system momentum in collisions. Is there a general rule that we can apply that we saw worked in explosions, but doesn't work in a wider sense? So you went through and did a pivot interactive here where you measured the initial system momentum and the final system momentums, and you made a graph of your final system momentum in grams centimeters per second, just to keep the units simple and pivot, and graph that versus your initial system momentum, also in grams centimeters per second. And if you did it all right, hopefully you got a graph that looked somewhat like this. Now, there were some negative ones and there were some positive ones, right? But they were either both negative or both positive. So we were always in the first or third quadrant. But it ended up being, hopefully, a pretty linear graph that went through 0, 0, which tells us that those two things are proportional to one another. So that's kind of interesting. If your initial system momentum is twice as big, so will your final system momentum be twice as big. But can we make that a little bit more useful? Well, we can. We can take this linear graph and turn it into a y equals mx plus b math model. The y variable is, of course, the final system momentum. Notice here I'm using a capital P, right, for system momentum. And that's going to equal your slope. Now, what was your slope? Well, let's take a look at some slopes. These are actually from last year. But if we look at the slopes, you'll see that they're all pretty close to one another. Right? All pretty close to one another. And what are they pretty close to? Well, take a look at the average, 0.993. That's pretty dang close to what? 1. So some pretty good experimental evidence here that the slope looks to be about 1. Well, that's a good slope, right? But think about the units. Slope is rise over run, where our units of rise are grams centimeters per second, but our units of run are also grams centimeters per second. So what happens to the units? They cancel. They become a 1. So that means that our slope here is probably the world's best possible slope, 1 with no units. That's going to make a little math magic in a moment here. What's the x variable? Well, that's the initial system momentum. And the y-intercept was, of course, 0. If nothing was moving initially, it's not going to start moving finally. So, or, sorry, if it was 0 initially, it could move finally, like it did in our explosions lab, but those momenta were always equal and opposite, so they added up to 0. So 0 initial system momentum, 0 final system momentum. But what happens when you multiply by 1? Absolutely nothing, of course, because 1 is the multiplicative identity. Therefore, not only are the final and initial system momentums proportional, they are also equal to one another. And look at your data sheet. Aren't all of your initial and final system momentums basically the same? They should be pretty close. I mean, after all, we're analyzing a video. Now, there is a little give on exactly the displacements and the times, right, that were in there, and but we still should be ballpark. I would hope pretty close to seeing that it actually was the same. Well, this is a very important law. Important because it's how we go about analyzing collisions, right? And notice here that we're talking about a quantity, system momentum, which stays the same. And in science, we have a fancy way of saying something doesn't change. We say it is conserved. Remember the law of conservation of energy? So this is our second conservation of law. It's called the law of conservation of momentum. That's what this is. Initial momentums equal to the final momentum. Little fancier language, it says in any closed, isolated system, the total momentum remains constant. Now, be careful. We have to have a closed, isolated system. What does that mean? Well, closed just means that the total mass doesn't change. So if we have a collision, we don't have a piece fly off that we don't keep track of. Oh, things can break up into pieces, but we have to keep track of all of the pieces. Right? This, of course, can get complex if you're in more than one dimension, but it can be done. Right? Isolated, well, that's something we used in energy. That means no external forces. Right? So as long as the forces are only between the objects in our system, and we don't lose any of those objects, well then, momentum remains constant. Right? And as you saw here, there wasn't an exception to that. The initial momentum and the final momentum stayed the same. And that's what makes it a very handy way to predict what's going to happen in collisions. Pretty much we're going to spend the rest of the unit looking at this law of conservation of momentum and what kind of predictions it can allow us to make. Now, one of the nice things we can do, as we did in the collisions lab, we can do a proof. But in this case, I'm actually going to take you through two proofs. They're related, but just different starting points, all right, to see this. First off, we're going to do a proof that's very similar to the one we did for collisions. If we were to actually throw some force probes onto these gliders, how would the forces they apply to one another compare? Well, of course, by Newton's third law, those forces would be equal and opposite. We've done that, lab. How about the times of interaction? Well, of course, they only interact with one another for the same amount of time. So that means, if we multiply here, the forces times the times would have to be equal and opposite to one another. But recognize this is impulse, a force acting over a time. Right? And so that means that the impulses are equal and opposite to one another. And if the impulses are equal and opposite to one another, then the resulting change in momenta must also be equal and opposite to one another. This, of course, is applying the impulse change in momentum theorem, which says that impulse is equal to the change in the momentum. Notice here, this is the force that the left cart puts on the right cart, which causes a change in momentum of the right cart. This is the force the right cart puts on the left cart, which causes a change in momentum of the left cart. Right? That's why the letters are the way they are. But here comes the key thing now. If the changes are equal and opposite of the two carts, then what's the total change? Well, the total change would be the sum, but they're equal and opposite. So that means they add up to 0. And so the total change in the system momentum is 0, means it doesn't change, it stays constant. So this is a little proof starting with Newton's third law and our impulse change in momentum theorem that logically tells us that we should have gotten what we got in the lab. Second way to derive this, probably more of the way that Newton actually did, and we're going to start with Newton's second law, but not the one that we use a lot, which is force is mass times acceleration, but rather the way Newton wrote it, which is that net force is the rate of change of momentum, the change in the momentum over the change in time. Yes, calculus people, this would be a derivative of the momentum with respect to time. Well, the net force that's acting, there's basically two kinds of forces, right? There could be external or internal forces. Right? Well, we said this was an isolated system, right? And so if this is an isolated system, there are no external forces. So then the only forces remaining are internal forces. That means forces between the objects, like the forces between the gliders. But we know those forces between the gliders, the objects in a system, always come in equal and opposite pairs because of Newton's third law. So when we sum them up, the net force would be 0. This is if we have a closed, isolated system, right? Isolated, there's no external forces to deal with, and the internal forces will always cancel each other out because they come in Newton's third law pairs. Notice, they don't cancel each other out on a particular object, right? One of those forces acts on the right object and changes the right object's momentum. One of them acts on the left object and changes the left object's momentum, right? But total in a system, we have to add them all up. And if the net force is 0, that means the rate of change of momentum is 0. And the only way for the rate of change of momentum to be 0 is if the momentum itself is constant. Okay? Which is what the law of conservation of momentum says. Calc people, for a derivative to be 0, right, the function has to be constant. Right? The derivative of a constant is 0. The rate of change of a constant is 0. So these are two different proofs, Both equally good, just different starting points. Although you notice here, this is really where we derive the impulse change in momentum theorem anyway, right? So just different ways of going about it. But in both cases here, we get that the total momentum has to stay constant. The system momentum has to stay constant if we're in a closed, isolated system. So once again, we have that glorious opportunity of having theoretical, logical conclusions matching what we actually see in our lab in reality. That's what makes science, right, such a powerful tool, right, because we match theory to reality. Right? And we can go back and forth either way, right? Our theories better be backed up by experiments, and our experiments better be backed up by theories eventually. Right? That's how science is done. Now, you may have noticed that we did do two kinds of collisions in that pivot. Right? And those were the magnet ends bouncing, and then the putty, right, which stuck together. Now those are typical of two kinds of collisions, and you're going to hear these terms thrown around a bit in this unit. The magnet ends are what are known as elastic collisions, or at least they're close to being elastic. Probably not perfectly, but close. For something to be elastic, not only is momentum conserved, because it's conserved in any closed isolated system collision, right, but kinetic energy is conserved. And that means there's no energy dissipated. There's no E-dis during the collision. Okay? Magnets are an approximation of that. Since the carts don't actually touch, right, we don't get frictional effects. There's no sound when they hit one another. There's probably very little thermal energy generated, all of that kind of thing, right? Now, most collisions are not elastic. Really, the only truly elastic collisions are subatomic particles and things like in particle accelerators. But we can approximate it, all right, in real life. If we're dealing with magnets, if we're dealing with ideal springs, right, that don't dissipate any energy, which, you know, your typical spring is going to be in the ballpark of. Maybe two billiard balls, pool balls hitting one another, right, that are very round and very hard, right, and they don't dissipate a lot of energy. A little bit, you can definitely hear them hit, right, but not a ton. Most collisions, to one extent or another, are what are known as inelastic. And inelastic collisions, momentum is conserved, but kinetic energy is not. Right? Energy is dissipated in some way. It's usually stored as thermal energy, sound, deformation of the objects. You know, it's changing something else. Right? And remember that dissipated energy is no longer useful to our mechanical system. Right? So in a real collision, even in those, we're going to examine exactly how elastic were our collisions that we've been doing. Right? But in most real collisions, all right, they're going to be inelastic. So when doing physics, you never assume that a collision is elastic, right? You need to be told that a collision is elastic, or you need to be, given some reason to believe that it is. Usually, if they mean for it to be elastic, they'll tell you it's elastic, right? Most collisions are going to be inelastic, so kinetic energy won't be conserved, but momentum still is. And that's the whole reason why we use this quantity of momentum. Knowing something momentum by itself is not all that useful, but using momentum to analyze what happens during a collision, that's vital, right? And you can do that in pretty much any situation as long as it is a closed, isolated system. Whereas energy, right, you have to have, perfect collisions, elastic collisions, for energy to be very useful. Right? So we're going to, as I said, start to apply this now and apply the law of conservation of momentum to many different collisions for the rest of the unit.